So let's start our today's lecture. In the previous lectures related to chapter 6, we studied the construction, working and symbols of GFET and depletion type MOSFET. Today we are going to study the working, construction and symbol of enhancement type MOSFET. But before proceeding to our current topic, today's topic, let's summarize the results which we gained in the previous lectures of this chapter. The main takeaway from the previous lecture is that in JFET there is only one mode of operation, which is called depletion mode, while in depletion type MOSFET there are two modes of operation present in its working, and which are called as depletion mode and enhancement mode. In depletion mode, the number of free carriers in the channel increase, while in number of free carriers in the channel decrease in depletion mode, while in enhancement mode number of free carriers increase in the channel. Hence, in depletion mode, the drain to source current is reduced, while in enhancement mode, drain to source current is enhanced. So now let's start explaining the basic construction of an enhancement type MOSFET. In enhancement type MOSFET, one thing which we must know is that there is only one mode of operation, which is called enhancement mode. In enhancement type MOSFET, there are no two modes of operation present. So let's focus on the construction of a typical N-channel enhancement type MOSFET. It has a P substrate, which is also called a body, and this body is made up of P-type semiconductor, while there are two N-channel material embedded in the P-channel substrate, and metal connectors are connected with these two N-channel uh, N-type semiconductor portions. The upper portion connected with metal connector is serves as drain, while the lower N-type material connected with the metal connector serves as source. And the P-type material is insulated from the metal terminal of the gate so that no current can pass from gate to the body. And this insulating material is silicon dioxide. So the main difference is, as you can all see, there is no channel present. In GFET and depletion type MOSFET, channel is already present through which drain to source current can flow. But in this case, there is no channel. This is the main difference in the construction of depletion type MOSFET and enhancement type MOSFET. So now look Now we are going to study the basic equation and its characteristics. For this, let's focus on this diagram, how channel is formed in the enhancement type MOSFET, because channel is not already present. So let's see how this channel is formed. So if VGS is set at 0 volt and voltage applied between the drain and the source of the device of figure 6.32. So gate to source voltages are set to 0, and an external voltage source battery, you can say, is applied between drain to source terminals. So what will happen in this case if gate to source voltage is 0 and drain to source voltage is applied? Will there any current flow from drain to source? The answer is no, as there is no channel. For the current to flow between drain to source, there must be a channel. Since there is no channel, it means no matter how much value of the voltage you increase from drain to source, no current will flow from drain to source, as there is no channel. While in case of depletion type MOSFET, there was channel present. So you when we increase the voltages between drain to source, the attraction power forces increase, and the more and more majority carriers are attracted by the drain in case of N channel depletion type MOSFET. So the current from drain to source goes on increasing until the saturation point is reached. While in this case, when VGS is at equal to 0, no current flows from drain to source. This is the main difference. So in order to flow the current, in order to current to flow from drain to source, we must apply some sort of potential between gate to source terminals. So let's say we apply positive voltages between gate to source. Now what will happen? Positive voltages have been applied between gate to source. What will happen? Gate become more positive as compared to ground. Hence, the holes, which are the majority carriers in this p-type substrate, will be pushed deep into the substrate due to the repulsive forces exerted by the positive potential at the gate terminal. As a result, there will be majority of minority carriers left near the gate boundary. As you can see it here, there is a quite large number of minority carriers left in this region, while all of its majority carriers are pushed back deep into the P substrate. So in this paragraph, this phenomena is explained. The positive potential at the gate will pressure the holes because like charges repel deep into the substrate along the edge of the silicon dioxide layer. Holes are pressed into the substrate due to positive potential applied at the gate terminal. The result is depletion near the silicon dioxide insulating layer wide of holes. Hence, near the silicon dioxide insulating layer, depletion of holes occurs, while the number of electrons goes on increasing. So, how does this is achieved? That number of electrons near this silicon dioxide layer goes on increasing because these attractive forces or the minority carriers. This potential positive potential will act as attractive force by the minority carriers of the p substrate, and the minority carrier will be attracted near this H. These electrons cannot cross this silicon dioxide insulating layer because otherwise these electrons might be attracted to this gate terminal. To prevent this and increase the input impedance, we have inserted the silicon dioxide insulating layer. So as the value of VGS is increased more and more electrons are accumulated near this silicon dioxide insulating layer, and more holes are pushed deep into the P substrate material. Hence, there will be a time when a channel will be induced between these two n-type regions due to the increased potential between gate to source terminals, positive potential. And this induced channel will now can serve as a path for the current to flow from drain to source. So we must know what is the minimum value at which this channel is induced, which can support the path for the current to flow from drain to source. We must know this minimum value of gate to source voltage. This minimum value of gate to source voltage is called as threshold voltage. Since the channel is non-existent with VGS 0 and enhanced by the application of positive gate to source voltage, this type of MOSFET is called as enhancement type MOSFET. Both depletion and enhancement type MOSFET have enhancement type regions, but depletion mode is not present in enhancement type MOSFET. So what will happen if we increase the voltage beyond the threshold voltage between gate to source? It is obvious that the density of free carriers near the edge of silicon dioxide layer will increase and will keep on increasing, which will result in increased drain to source current. However, what will happen if we hold the gate to source voltages constant, increase the drain to source voltages? It is observed that as we make the voltage between gate to source constant and slowly increase the voltage between drain to source, the current also goes on increasing between drain to source until a saturation point is reached, similar to the saturation points which were reached in JFET and depletion type MOSFET. So this situation figure 6.34 shows the saturation point in which the width of channel is reduced, or you can say pinched off at near the drain terminal. We can apply KVL to find the working equation of enhancement type MOSFET. VDG is equal to VDS minus VGS. VDG is equal to VDS minus uh, VGS. Simple KVL must be applied to find this equation. It means VDS is resolved into two components, VDG and VGS. So if we want to find VDG, we must subtract VGS from VDS. So if we subtract VGS from VDS, we get VDG. So once saturation is reached, any further increase in VDS at the fixed value of VGS will not affect the current flowing from drain to source. Current will remain same at saturation point. So what will happen if we increase the drain to source voltages more and more? So hence, after the saturation is reached, any further increase in the value of VDS will only increase the reverse bias voltage which is applied at the N-type drain and which is applied at this PN junction, because N-type material is provided with positive terminal of battery and P-type substrate is grounded. which is which fulfills the condition for the reverse biasing of this PN junction. Same. Hmm. So any further increase in VDS will only increase the reverse bias voltage at the PN junctions, and a point will come when these junction will break and a huge current will flow from drain to source. Hence we can plot the drain characteristics of enhancement type MOSFET. At the x-axis we have drain to source voltages, and at the y-axis we have drain to source current. So as you can see, these characteristics are drawn at different gate to source voltages. So when the gate to source voltage is +3 and it is fixed at this value, the increase in drain to source voltages will only increase in the power consumption of this MOSFET, while the saturation current almost occurs at 1.5 volt of VDS. As we increase the VGS, the saturation level of current goes on increasing. This dotted line show the value of the saturation currents, and if we draw the perpendicular from all these points at the x-axis, we get the value of the saturation voltage of VDS. So the trend is that as we increase the gate to source voltages and make it fixed and make them fixed, increasing the value of drain to source will increase the value of drain to source current, but a time will come when further increase in drain to source voltages will not result in increase of drain to source current, and that point is called saturation point. Saturation voltage is equal to VGS minus VT. And so we can summarize as for values of VGS less than the threshold voltage, the drain current of enhancement type MOSFET is 0 milliampere as discussed. A minimum voltage is required at the gate and source terminals to establish a channel through which a current can flow from drain to source, and if this gate to source voltages are less than threshold voltage, no current will flow. But for level of VGS gate to source gate, but for levels of gate to source voltages greater than threshold voltages, the drain to source current will follow this equation, where value of K can be found by this relationship, and where ID on and VGS
on are the values for each at a particular point on the characteristics of device. At any point on the characteristics, let's say we choose this point at this characteristic for VGS is equal to 7 volt. The value of ID can be taken as ID on and value of VDS by dropping perpendicular on the x-axis can be taken as VDS while the VGS on is equal to this value. Hence, for this characteristics, VDS on is plus 7 while the IDS on can be found at any point on this characteristic by dropping perpendicular on the y-axis. So let's say ID on is equal to 10 milliampere and VGS is equal to 8 for this characteristic we are talking about. Then value of can be found as this, and putting this value in this equation, the value of ID can be found as this. So in this way, for enhancement type MOSFET, we can find the value of drain to source current. So if we plot another graph between gate to source voltages and drain current, we will get this kind of transfer characteristics in which both voltages are plotted against drain current. First, these characteristics are plotted against drain to source voltage and drain to source current are measured keeping the VGS constant at plus 3, plus 4, plus 5, plus 6, plus 7, plus 8. And these characteristics are the graph between saturation voltages, saturation current, and the voltage between gate to source at which this saturation point occurs. Let's say for this characteristic VGS is equal to 4 and IDS is 1. So this dot is placed at this point for VGS equal to 5 for this characteristic. IDSS is 2 point something and this point is achieved and so on by combining by drawing a line through all these points we get a graph between VGS and ID. So P channel enhancement type MOSFET has the same working and construction. The only difference is all the currents and voltages are reversed in their polarities and substrate substrate is now made up of n-type material and drain and source regions are made up of p-type regions as shown in this graph in this diagram A. Again, in this case gate to source voltages will be negative and this curve will flip itself from the previous curve which was drawn for n-channel enhancement type MOSFET. Flip at 180 degrees around this y-axis. So these are the symbols of and general p channel enhancement type MOSFETs. With this lecture is over and this chapter is also over. Now we will start the DC analysis of MOSFETs in chapter number 7. Thank you very much.